Hello, my name is Kyle, and I'll be presenting a lecture on static stability and design characteristics of flying wings. So here's a preview of what this lecture is about. We'll define a flying wing, and we'll talk about some static stability equations, followed by different characteristics and advantages and disadvantages of those characteristics, and then we'll end with a real-world example. What is a flying wing? Well, the simplest definition is that it is an aircraft with no tail. I always learn a little quicker with pictures, so I provided a few examples of flying wings. The first was a U.S. military prototype built by Northrop in 1942. The second was a prototype built by the Horten brothers in Germany in 1943. The third example is one of the only manned flying wings regularly flown today. That is the B-2 Spirit, built by Northrop Grumman in the late 80s and flown in 1989. As you can see, they all have some common traits as well as a few differences. We'll talk about a few reasons why these aircraft were built the way they were, as well as a few drawbacks to flying wings in relation to conventional tailed aircraft. Let's go over the static stability equations and how they are slightly different for flying wings. Here is the moment coefficient buildup for longitudinal static stability. This is very similar to tailed aircraft, except of course the lack of tail contribution. There are fewer terms, which gives the illusion of simplicity, but practically this makes flying wings difficult to design. With fewer terms contributing to the pitching moment and shorter moment arms for each contribution, each term has more effect on the stability. The pitching moment for a flying wing is much more sensitive to center of gravity or aerodynamic center changes. Since the elevator is on the wing, any change in deflection affects the aerodynamic center, making this a complicated issue. So now we'll move on to lateral directional static stability equations. These equations do not look quite as different from conventional aircraft as the longitudinal static stability equations. Really, the only difference here are the assumptions and how the derivatives are built up. A lot of flying wings do not have a rudder control surface, so the last term is usually either removed or replaced by other control effectors. Some aircraft use differential thrust or split rudders, also called speed brakes, placed on the tips of the wings to help control side slip and yaw moments. Another typical design choice to simplify some things is the symmetric aircraft configuration. Now let's walk through those stability derivatives I had mentioned earlier and how they're affected by different things. The side slip contribution to side force is stabilized by the use of wing sweep, vertical fins, or an active yaw damping control system. The side slip contribution to roll is stabilized by wing sweep as well as dihedral. If the aircraft has a fuselage, then mounting the wings in a high wing configuration can also add roll stability. Side slip contribution to the yawing moment is affected by, again, wing sweep. Vertical fins also stabilize this derivative as long as they are placed behind the center of gravity. Since wing sweep has such a strong influence on flying wings, almost all flying wings that have pilots in the aircraft have some angle of wing sweep. This is because of the inherent stabilizing effects that swept wings have on a flying wing. It adds stability to the directional plane by creating a restoring yaw moment from a small perturbation in side slip. It also enhances lateral stability from the variation of lift between the left and right wings after a roll perturbation. Wing sweep also affects the longitudinal plane because sweeping the wing changes the lift distribution and thus the aerodynamic center. Usually it moves it backwards the more you sweep the wing. So wing sweep can be used to manipulate the neutral point to obtain either a larger static margin or a more stable aircraft in general. Even though wing sweep has a lot of benefits, there are a few drawbacks to using this as a design implementation. One major drawback is that the beneficial effects are dependent upon the coefficient of lift. So the yaw moment contribution is proportional to the square of the coefficient of lift. So it follows that because of this relationship, the roll and yaw moment contributions are small at small angles of attack. So a swept flying wing is susceptible to a neutral and sometimes unstable Dutch roll mode at high speeds where you have that low angle of attack. Some ways that the designers try to mitigate this issue includes an active yaw damping control system or adding a small anhedral to the wing orientation to try to counteract that effect at those certain parts of the envelope. All right, so let's move on to talk about two factors that make flying wings more desirable than conventional aircraft. They tend to have higher lift-to-drag ratio and lower wing loading factor than conventional aircraft of the same size. Lift-to-drag ratio is a useful non-dimensional characteristic that describes an aircraft's efficiency in range, endurance, and performance. Flying wings tend to have a lower parasite drag and higher lift compared to similar sized conventional aircraft. Parasite drag is primarily affected by the wetted surface area of an aircraft. So if the flying wing does not have a tail or fuselage, then it follows that they typically have much less wetted surface area. And so parasite drag is minimized. Induced drag, however, is proportional to the lift. So this means that flying wings generally generate more induced drag than conventional aircraft. This is mitigated through certain design choices such as wing sweep and the addition of winglets at the ends of the wings. A high lift-to-drag ratio means that flying wings have longer range and more endurance than conventional aircraft. I have provided the Breguet equations for range and endurance for jet aircraft to show that both range and endurance are directly proportional to lift and to lift-to-drag ratio. Moving on to wing loading. Wing loading is the ratio of the weight of the aircraft over the reference surface area of the wing and describes the weight per unit wing surface area of an aircraft. As shown in the picture, one can see that both the weight and the lift of this flying wing are well distributed across the entire platform, which means that flying wings tend to have low wing loading. For conventional aircraft, the weight is typically concentrated in the fuselage while the wings generate most of the lift. Conventional aircraft thus need more structural support to connect these two loads, lift and weight. So what does this mean exactly? Well, low wing loading means that flying wings can carry less structure and more of something else like fuel, payloads, or nothing, and save the weight. So because of low wing loading, flying wings tend to weigh quite a bit less than their conventional counterparts. Another benefit from low wing loading is improved rate of climb, since it is inversely proportional to wing loading. We will now move on to talking about two disadvantages of flying wings, small static margin and dynamic pitch instability. The fore and aft center of gravity limits are closer together on flying wings, which means that any weight change in flight, whether by fuel or other payload, has more effect on pitch stability of the aircraft. The neutral point can also change in flight. This is usually due to control surface deflection or a change in angle of attack. Deflecting surfaces can change the lift distribution of a flying wing. This can be mitigated by certain design choices such as wing sweep and airfoil selection. The second drawback of flying wings that I'll talk about is the inherent dynamic pitch instability. Both the short and long period modes are usually underdamped in certain flight conditions and could be unstable in other flight conditions. Another aspect of the short period mode that the flying wings exhibit is a susceptibility to angle of attack oscillations after a gust. If an untrained pilot tries to correct this oscillation, he or she could actually induce larger oscillations or, in a worst case scenario, divergence from controlled flight. This phenomenon is called pilot-induced oscillation. Luckily, there are a few methods to stabilize dynamic pitch modes. The main method used today is the implementation of a digital flight control system with the ability to compensate for gust loading or other undesirable tendencies much more quickly than a human pilot. A computerized flight control system is the best method to counteract dynamic pitch instability. After going through a few advantages and drawbacks of a flying wing, let's look at a real-world example where some of these are visible. I'm going to pick that third picture I had at the beginning. The B-2, nicknamed the Spirit, is developed for approximately 10 years before flying for the first time in July of 1989. And it took a whole 10 years later before the B-2 would debut in combat for the first time. The B-2 is a long-range strategic bomber that was designed as a flying wing. A few design traits of the B-2 that tie back to what we've talked about earlier include wing sweep, split rudder yaw control surfaces, and a digital flight control system. We can deduce that wing sweep added stabilizing contributions to the yaw and roll moment side slip derivatives. The split rudder yaw control surfaces were part of an active yaw damping control system, and they functioned as speed brakes as well, which can act as the vertical fins we talked about at slow speed, improving lateral directional stability during landing and takeoff. The digital flight control system attenuates the pitch instability characteristics. So you can see that even though flying wings are dynamically unstable in pitch and highly undamped in roll and yaw, the benefits of long-range, high endurance, combined with the design characteristics we talked about above, flying wings certainly have clear advantages over conventional aircraft for certain functions. So hopefully with this, you'll be more informed on the differences between flying wings and conventional aircraft.